Hello, am I audible?
जी sir, yeah.
Okay. Hello, good morning and a warm welcome to everyone present over here. This morning is very energetic morning to all of us and all science lovers because this day is celebrated in India every year on 28th February to mark the discovery of Raman effect by invention Indian scientist Dr. Chandrasekhar Raman. On 28 February 1928, for this discovery, he was awarded by the Nobel Prize in Physics in 1930. Also to motivate and encourage students about science and technology, Educational Institute celebrate this day. Our IIMT College of Engineering Greater Noida has organized this small function, and for this purpose today we have gathered here to celebrate National Science Day in presence of Honorable Chief Guest Professor Ajay Tyagi ji from Banaras University, Varanasi. On behalf of IIC coordinator and IIMT College of Engineering Greater Noida, I would like to welcome today's chief guest, Dr. Ajay Tyagi ji. Sir, please share the valuable ideas with us and motivate our students also. Thank you, sir. Please, Dr. Tyagi, sir.
Thank you, sir. Thank you very much. I'm just going to, and firstly, I just want to convey my sorry because I'm late. We have some development in the department in my lab, and that is definitely related to the science. And it was the very fortunate day for us that we could make it on today, 28th February, on Science Day occasion. So it was by chance. Means we were not expecting. We were expecting this consignment something after lunch, but they came earlier, and I have to stuck because we have to transport the thing in the building. So anyway, but I'm okay now. So I'm going to share the slide, and just let me know if you are able to see it. Can you see this, sir?
Yes, sir, exactly. Very clear.
Okay. Okay, so should I start?
Yes, sir, please start, sir.
So just for a thought, I plan this title of this talk, and for naughty and for neutrons, a fantastic tool for research. And I will tell you why it is naughty and why and for neutron are correlated to each other, and why it is a fantastic tool for research for everyone. Not like me, I'm working in the field of experimental nuclear physics, but it is good for everyone. And I will somehow try to correlate what I am going to present to you today, and slight correlation with what Raman Sahab did. So I'm not saying that I am doing the same thing, or I'm just comparing, but I will just try to correlate the theme of today's this Science Day, National Science Day, and the work he got Nobel Prize. So I'm just trying to correlate the theme of today's presentation. So is it okay? Can you see this CV Raman picture? It will make sure that I am shifting my slides properly. Is it all right, sir? Can you see the next slide?
Yes, sir.
Okay, so now I'm confident that you will see all the slides in proper way. So it was an idea in 1986 by National Council for Science and Technology Communication. They requested to Government of India that we should celebrate Science Day in India, and it was decided to make it on February 28 as a National Science Day, because on the same day we got the Nobel Prize. And this, if I am correct, so this was the fastest kind of research which got Nobel Prize in the fastest way. It took very less time, the time it published the results and to receive the Nobel Prize. So that duration was smallest in the history of Nobel Prize, what I got from literature. And consequence to this Nobel Prize, Government of India honored Raman Sahab to Bharat Ratna. So there are a lot of things I was reading. I got opportunity due to this lecture to read about Professor C.V. Raman. I'm going to share few things which may be very motivating for students and even for us also, anybody who is working anywhere. So that gives you kind of moral boost and take care of your confidence level also, what kind of confidence he has. So first thing was that Raman Saab didn't have a PhD, regular PhD. So he was not kind of PhD person. So he basically qualified the Indian Revenue Services at that time. And after that, he was doing research. And when he was appointed first time Palit professor in Calcutta University, so there was a opposition group, and they said that how you can make a guy professor who doesn't have a PhD. So then at that time, Vice Chancellor arranged a DSc, honorary causa doctorate degree to Dr. Raman, and he got this doctorate. So that was a funny story that the guy is able to get the Nobel Prize, but since he doesn't have a PhD, so he cannot be a professor. So that was one interesting thing. Second interesting thing was that the salary he was getting in at that time as a revenue officer and what he was getting as a professor in Calcutta University, so that was exactly half. So that is very interesting that he switched over to a research position at half salary. And another thing which I just want to quote as it is this. In a speech at University of Calcutta, he said, "I'm not flattered by the honor fellowship," because he was become this fellow of Royal Society of London. So he said that I'm not flattered by the honor of this Royal Society fellowship done to me. This is a small achievement. If there is anything that I aspire for, it is the Nobel Prize. You will find that I get that in 5 years. And he could not wait. The interesting thing was that when he submitted his result and he was nominated for Nobel Prize, he didn't wait for the result and he booked ticket because he was aware if he will not book in advance, so he will not able to reach to the event to getting award, Nobel Prize. So he booked the ticket in advance and definitely he got. And when he was questioned that if you were getting this last year, so what he said, then I should have shared the Nobel Prize with Compton, and that I don't want to do. So this is fine for me because now I am the single owner of this award. So this tells about the kind of confidence he has and the affection he has for research. So now I will just brief in little, because this is not my subject, what he did about Raman spectroscopy, what we say Raman scattering or Raman effect. But this is the point where I can correlate myself, my talk of today's to this thing. So basically, Raman scattering is the second part of what we talk about Rayleigh scattering, due to which we see our sky blue. So Rayleigh scattering is basically elastic scattering, and Raman scattering, or what we say Raman effect, is basically inelastic scattering. So when we talk, we already have an idea about scattering in our 12 days and in graduation, that elastic and elastic are two different things. And in elastic scattering, we have conservation of linear momentum as well as energy. But in case of inelastic scattering, the energy conservation is not possible. It is not the same on the right hand side or left hand side, and it depends on what kind of situation you have on the left hand side or right hand side. It is kind of endoergic or exoergic kind of reaction. So the question comes that where you are losing the energy. So that energy is going to use to excite the molecule, or you are getting it in a excited state atom or molecule. So you are getting it, or you are losing it to excite it, or you are getting something, you are hitting it in an excited state and then it is coming in the ground state. So you are gaining something. So in that way, you have a kind of situation that in one case you are getting less energy or a low frequency, or in another case you are getting high frequency or high energy or shorter wavelength. So this is the situation. If you see here the Rayleigh scattering, the y-axis tells you about the energy, and this is your ground state. These are vibrational states, and this is the virtual state. So if you shoot something with photons, so the molecules go in a higher excited state. So it will start from ground state, go to the virtual excited state, and then it comes back from the same excited state to the ground state. So from where it started the journey, it come back again to the same place. So this is Rayleigh scattering and known as elastic scattering. But if you see here, so this guy starts from here, goes to the excited state, and then decays from here, but doesn't come to the ground state, right? And so this is known as Stokes line. And when it goes from excited state to this place, and it comes from here to here, so what you see that it is going from 0 and going to some E1, but it is coming from E to it is going from ground to E1, but it is coming from E1 to E. So this is the minus thing. So you are getting energy here because you are not coming here. So this line will be of longer wavelength, or say less energy or less frequency. But here you see that something you strike off, you shoot your photon on a molecule in already vibration state, and it you shoots up to this state, and it comes from here to here. So you are getting more here. So the anti-Stokes are for shorter wavelength or higher energy or high frequency. So this was the kind of study which is mentioned under Raman effect or Raman scattering. And this was the simple experiment. You have sunlight and you are collimating it through this telescope, and then you're passing through the filter and you have the samples. And the beauty of this experiment was what he got on Nobel Prize, that this is true for solid, gas or liquid. So anything, and you can see that part of Raman scattering. So what I mentioned, that I will just correlate with this Raman effect. So I'm not going to do anything with photons because I'm not a person of a spectroscopy, but I will talk about scattering in nuclear physics, elastic scattering, inelastic scattering, and there we will talk. Here the shooting particle is photon, but in my case, in the coming talk, the shooting particle will be neutrons, right? So we will talk about what you can do neutrons, how you are obtaining neutron, what are the restrictions when you are getting neutrons from radioactivity, and how you are getting a control beam of neutrons, and how do you do studies, different kind of things. So how much time you will provide me, the organizer. So I will go through. I will request you that you can stop me anywhere you are not getting, I am slow, you are not liking my voice. So you can tell me, you can stop anywhere, you can put any question. Most welcome, I will be happy, because in this online thing, I cannot see you guys. So I cannot assess your expression. So you can stop me anywhere. You can put your comments, anything. I don't I don't mind at all. So is it okay? Was I audible to everyone? Everything was okay in terms of audio and video?
Okay, sir.
Okay. So I will just spend few seconds. So this is the Government of India plan that, okay, if we are celebrating Science Day, so they are not saying that everybody should work in the direction of the theme of Nation Science Day, but every year, just to cover every aspect of science, they made a kind of theme of every year Science Day. So I just put this from web that, excuse me, what I got, I don't know, it was based on theme before 99, but from website I got from 99 onward. So you can see a lot of things. And this year we are going to make for integrated approach in SNT for sustainable future. So I'm going to make correlated my talk for sustainable future also in terms of SNT and in terms of what Raman Saab did. So he worked on scattering process through photons. I'm going to talk about scattering when you are using neutrons. So both have their own importance in the field of experimental nuclear physics and spectroscopy. Excuse me. So this is a simple description of radioactivity. We have something known as radioactive material, and it is emitting particles. It depends whether it is a alpha source or gamma source or neutron source. So it has a half-life. In that period, it becomes half of its original position. Suppose I have 10 gram now and I say the half-life is 1 day. So in 1 day, in 24 hours, from 10 gram, it will be 5 gram. And subsequently it will be half and half and half with time, and correspondingly its intensity will be lower down. Intensity, when I say, so intensity means if I have alpha source, so it has a emittance power. Like in college or university labs, we have very low intense radioactive source, but if we go for a research purpose, so we have very high intense source like 10 to the power 5, 10 to the power 6 particle per second. So it is a spontaneous process, but the problem of this spontaneous process is that it's a kind of mixture. Means you have all kind of energy of particles. If you are saying to me, I want to do with this particular energy reaction, so I'm not able to do this. But if you say that, okay, you are happy with 0 to 2 MeV neutron or 0 to 2 MeV alpha, I don't care whether I am interested in 0.5 or 1.5 or 1.4 MeV. So this is good. Radioactivity is good, and you can do a lot of things. Even people were doing a lot of things, like Rutherford scattering was done through alpha source, and the treatment was going on through cobalt. In olden days, you can see pictures. Even the patient was recovered, but the medical practitioner was died because he consumed a lot of radioactivity. So that was not a proper one, but at the time it was the only knowledge based system. So what we know, so we were using that thing. So those are the constraint of radioactivity or radioactive source, that you cannot make it monoenergetic. Like you cannot pick, I need only this energy, I don't need the rest one. So it's a kind of mess of energy, 0 to maximum, and that's it. So that is the limitation of radioactivity or radioactive source. So this is the nomenclature we use, like you have uranium-238, it emit out the alpha. So they are daughter nuclide because they are, and this is known as parent nuclide. So these are different kind of types of radioactive decay, like carbon-14 decays through this, and beta particle. I am not adding here neutrino and antineutrino because that is not the theme right now. I am just interested to show about the decay process through radioactivity. So this is the example of beta decay in terms of radioactivity. Then you have how your gamma particle emit out. So gammas are almost no charge. There is no charge. They are energetic particles because they takes care of this de Broglie things, right? So we use them in different kind of research. So these are, again, you can obtain from radioactive sources. like sodium and cobalt are the good emitters of gamma rays. Alpha, as I mentioned, so we have this americium source. It emits out alpha particles. So you can get alpha particles from americium as a radioactive source. So this is the kind of table when I say that, okay, I am paranuclei and I am getting this particle. So this is my daughter nuclide, so alpha. So how much A, the mass number, and Z, so everybody knows about this. So this is the particular example of alpha decay. This is beta decay example. This is when you are getting a photon. So you see the difference in these two pictures, alpha, beta, and gamma. Here you are getting a particle, here alpha particle, here beta. Here we are getting photon, but the difference here and here is that you have a difference in A, -4, -2 in Z, here 0 in A, but variation in Z +1. Here both are things are 0. So you see there is 0. So you will say there is no change. It is 0 and 0. So what new thing are we are getting? So just see here that this is an excited state and this is in stable. So it is the same thing what happens to human being when you are excited state. So you have to release something. Then only you will be in a ground state or a stable one. So similarly, our nuclear system do the same behave, that if they are excited, you shoot something on them, they are in excited state, they will come down in the ground state by emitting a photon. So this is the photon emission or gamma emission. So this is kind of tabulation of radioactive decay. When I talk, because now I have to pick my talk. So when I talk about N4 naughty, N4 neutron, so I have to tell you why they are naughty, and I have to describe different kind of community of neutrons. Every neutron is not same kind of neutron. So neutrons are distinguished basis on their energy. So if I say that my neutron is something like 10 to the power -6 order of electron volt, so it comes in the category of ultra cold neutron. It is not like that it is kind of freezing neutron or it will give you kind of icing experience. But based on their energy, they are known as ultra cold, cold, thermal, epithermal, two relativistic neutrons. So when I say relativistic, so means you are going higher than order of velocity of light. So as a guy of experimental nuclear physics, so this energy range start for high energy people from GeV, or even if you go for TeV, so this is for high energy people. This range is for us, means from here to there we are experimental nuclear physics people, and if you are going in GeV and TeV terms, so this is for heavy ion or high energy people kind of interest. So this is what I mentioned in my first slide when I started radioactive. This is the disadvantage of radioactive source. You will get a spectrum, means you will get this kind of energy, this one, this one, this one, this one. So there will be an army of different capacity soldier having different kind of capacity of soldiers. You have the army. So you cannot pinpoint that, okay, I want to use 5 MeV neutron or 6 MeV neutron. So that's the problem. Another problem with neutrons is that you cannot produce neutron in a single shot. So here you will see that you have this source, beryllium source, boron source on alpha. So for that you have to make a kind of sandwich. Suppose I have a source here, I have a source here. So I need one source as a alpha source. So this is my alpha source. So I will stick with this. So alpha will come from this red one and it will go to the yellow one. Alpha will strike here and then you will see the neutron. So it is a two-step process. You cannot see directly neutron. There is no mechanism to get neutron like alpha or gamma. Alpha is coming directly from americium. Gamma is coming directly from sodium or cobalt. But neutron you cannot get from a single system like americium or sodium or cobalt. For that you have to sandwich two items. One will be alpha emitter and alpha will come and hit to this, and with that you will get a neutron. So this is the story of neutrons. So that's why the neutron business is quite complicated, because it is a two-step. Firstly you have to get a charge particle, then you will get the neutron. So it's a two-step process. Charge particle production is a single step process. So I hope I am making some sense and I am not making kind of very boring talk. I need your comment. because it's a blind talk. I'm not able to see anything. So you have to tell me something. Sir.
Yes, sir.
Is it going perfectly in your way, sir?
Perfectly, sir. Perfectly.
Okay. Sir, you can stop me. You can correct me anywhere. If you
Okay, sir.
find,
Okay,
yeah,
sir.
because I cannot see. I have made my window large. So I don't see anybody face. Okay. So it's a
Okay.
kind of blind situation for me. So you can call me if there is some obstacle from my side, because otherwise I have a doubt that I speak for 10 minutes and nobody is able to listen. So just ring me or on my phone or just stop me. Okay. Thank
Okay,
you
sir.
very
I
much,
will
sir. Thank
inform
you.
you, sir.
Right,
Okay,
sir. Thank you.
please proceed, sir.
Yeah. So see, this is the kind of sources, neutron sources, their energy, how much energy you can get. So when I say average neutron energy, so this is 4.2. So it means you will get a bunch. This is the maximum average energy you can get, but you will not get 4.2. It will have a combination of all kind of energy. In 2.5, you will have average maximum 2.5, but all 1, 1.1, 1.25, 1.3. So that's the trouble with sources, that you cannot pick the single energy particle if you are interested. If you are just interested in radiation, I don't care what energy it is. I am interested only in neutrons, so that's fine. Then you are good. So this is spontaneous fission sources. These are californium and plutonium, uranium. So these are the half-life of californium. So now the point comes that if I need a complete liberty for neutrons, if I say I need 2 MeV, I need 3 MeV, I need 2.5, I need 2.1, I need 2.2. So then I have to make a accelerator based facility where I can produce the neutrons. So you can see this is a typical reaction. This is a typical reaction. So these are four fundamental nuclear physics reactions. With the help, you can obtain neutron. Now question comes that why I am showing you four different reactions. So four are, the reason behind four is that firstly the availability. I want to go for a good restaurant, so I should have plenty of money. First thing is that. Second is whether I am capable to digest this food or not. Suppose I am having lot of money and I am a vegetarian, but all the restaurants in the city are non-vegetarian. So that is of my no use. I cannot use the money. So as a experimentalist, I have to see all the if and but, the support and the odd things you have in your lab or your university or institution or your country. And the third thing is the accommodation, the space, the infrastructure, the expertise. So based on that, and the most important thing, the energy interest, whether you are interested in 2 MeV range or you are interested in 25 MeV. Suppose you go for this reaction, you establish everything, and next day you come to me that you mentioned four reactions for neutron production. I need 25 MeV, but this is not giving more than 6 MeV. So I will say that you have to see the Q value of the reaction. You cannot go. So only thing is, if you want to get maximum, so you have to pick this reaction, because here the Q value is 17.6 MeV. So this is the problem. So if you will pick this, so I cannot go more than 6 MeV neutron. So here you see the interesting thing, how you will get a neutron. You will shoot your proton on tritium. This is the isotope of hydrogen, and you will get a neutron. So the question comes, how you will get a proton then first? Energetic proton. So to get a proton, you have to produce proton first. So you have to establish an accelerator and you will obtain a proton, and then you will shoot this kinetic energy proton to the tritium and you will get a neutron. Similarly, this is known as DD reaction. You will shoot a neutron on a neutron and you will get a neutron. So you have to produce firstly neutron. So today what machine I got? So we got a DD facility and it is in collaboration with BRC. BRC give me this machine free of cost. It costs something in crores. And because we have a building and I have expertise, so this machine is here in BHU in my lab. So you are most welcome. Anybody Doesn't matter you are from nuclear physics, it is useful for a person from medical to agriculture, material science, biophysics, chemistry. Anybody can come who is interested in 2.45 neutrons, 2.45 MeV neutrons. You will get in a second 10 to the power 9 neutron per second. So you can contact to me. I will, if I will have some time, so I will show you the pictures how we came in the morning at 7 here, and it took almost 4 or 5 days because it had to move with a very slow speed because the equipment was very sensitive. So today it's reached, and now safely it was installed in my lab. That's why I was slightly delayed. So these are four fundamental reactions. This is proton on lithium. When you are interested in neutron production, so you can go ahead with this reaction, and you can fix your neutrons. So this is your choice based system, what energy you need and what kind of facility you have. If you have a proton production, you go for this, or you go for this. If you have a neutron facility, so you can go for this one. So now I come on this part, what I was trying to correlate, because every time when you speak and you have some kind of reason to attend that meeting as a participant or as a speaker, so you have to connect the theme of the conference and the topic and the feeling of the audience. So when you go for nuclear reaction with neutrons, so you have different kind of mechanisms. So first one is elastic scattering. So as I mentioned, no change. The particle, incident particle, and the target is same before scattering, after scattering. So in terms of shape and energy, so it is known as elastic scattering. If the shape changes after scattering and energy also, so then it is known as a inelastic scattering. I will go in detail what is the meaning and how it looks exactly. Capture is kind of fusion. When it takes up your thing inside the target, so it is completely changed. I will show through some cartoons how it goes. Nuclear fission is that when neutron is shoot down on a heavy target, so it makes 3 neutrons and it goes through chain reaction, and it is used in reactors. So that's why I told you that I'm going to connect, because when we talk about sustainable mode, so we have 3 major sources of energy production. The water is one, the coal, and the reactor based system. So reactor based system is more sustainable in my thought, because I want to preserve my fuel. I want to reserve my coal as much as possible. There are 2 reasons. One is that it is in limited stock. Second, there are a lot of issues related to pollution, but this is a clean business. Though it is a sensitive business, but it is a clean business, more powerful than coal one and water one. So that is the kind of correlation of my talk towards the sustainable thing, that this is the demand. Even I spent 4 years in US, so even US is going to be leading personality in terms of reactors one. They are planning to go for power production through reactors. I tell you that India is the boss in terms of reactor technology worldwide. Means they appreciate worldwide whenever you will go. So everybody appreciate Indians development in terms of reactor technology, and they hire people from India because they know that they have really hardcore expertise. Fusion, when you have your 2 small nuclei and they collide at high energy, so they make a new one. But this is the kind of basic nuclear reactions. But we will focus ourselves on this elastic and elastic scattering initially, and when I have time, so I will go further to cover capture and fission also. So I think as a student or as a faculty of non-nuclear physics background, I will able to convey my thing about elastic, inelastic, and capture and fission from these diagrams. So just see, don't read, don't listen to me, just see the picture. Here you have a neutron showed by the green color. The yellow one is the target. You see, you hit it, and then you see the same thing. So you can see there is no change in color, no change in shape. The same thing with neutron. So perfectly all right. So energy is not changing. So this is all right. You shoot with 2 MeV, you are getting 2 MeV. The shape is same. So this is non-elastic scattering. Now I'm going to put a question on you guys. You are making a collision here. what difference you see in this and this picture? Anybody? Don't take care of your faculty. Just tell me the difference in this picture and this picture. Don't put your brain, just by common sense. What difference you see in this and this picture? Anybody? Any student? If there are students, what is the difference you are able to see? No physics. Sir, are they able to hear me or not? Because there is no response.
Sir, all the persons listen carefully. I think they are thinking about that.
नहीं, इसमें कोई ज्यादा बड़ी बात नहीं थी. देखिए, ये मैंने एक रेड स्पॉट दिखाया है यहाँ पे. तो रेड स्पॉट इसलिए दिखाया कि जब हम गुस्सा होते हैं, एक्साइटेड स्टेट में होते हैं, तो हमारा चेहरा लाल हो जाता है. जस्ट इंटेंशनली आई मेड इट. सो बेसिकली ये लेमन लैंग्वेज में बता रहा था, बट दिस इज इन एक्साइटेड स्टेट. सो ओनली डिफरेंस इन elastic versus inelastic is that when you shoot, so it goes in a higher excited state. So that's the reason that you don't see the same energy. So you have some plus minus in the conservation thing. So you are not getting the same energy because you put some amount in the excitation to send this guy in the excited state. And when it will come down, so it will emit out some photons also. In capture reaction, you see the difference that the size of this one is bigger than this because it consumed to this poor neutron inside its stomach, not stomach, in the nucleus. So this is bigger one, and this will emit out a photon again. In fission, as I mentioned earlier slide, it makes collision scattering, and then you have 3 neutrons, and it goes in a chain reaction process. Now there comes a utility point that when you do this kind of that kind of reaction, so what is the importance for a common man? So when we do elastic cross section measurement or elastic scatterings, so we use that data in neutron transport code and energy loss, which is very useful inside the reactor. So if my friend is going to design a reactor, so he will contact to me because he knows that Ajay Tyagi is working in elastic cross section measurement. So he will take, or he will ask me that I need this material elastic cross section because this material is going to use in reactor, and reactor is going to produce the energy, and that is a sustainable mode of energy. So as a person of this field, I will try to provide the best quality of data. I cannot provide a data of 100% error. So my expertise is that I could provide a very precise data to the guy who is going to design the reactor part. Similarly, if somebody asks for elastic cross section, so there are a lot of gamma production, so that creates a kind of heating. So how much heating will be there? Accordingly, you have to take care of the cooling inside the reactor. So you have to provide a precise set of elastic cross section data also. So those are the things which are extremely correlated with each other, and a illiterate person cannot understand that what is the motive of research, but one end of research connect to the ultimate end which we are getting at our home. But somehow as a non-science student, non-science social guy or citizen of a country, I cannot understand. But I think as a science student, we should have slight feeling that what is the fundamental role of research R&D in the development of any country. So that is the kind of thing I'm just trying. I don't know how much I am able to convey to you, but this is the only point that whenever somebody starts from scratch and go up to that point, so it's a kind of continuation. So somebody next is waiting for that information and he will pass it to another one. So they have their own expertise, and to be get expertise on a very small region, if you are getting in your lifetime, so I think that is very commendable because it's a vast area. You cannot do many things in your one life. So I am working at University of Kentucky also in collaboration of that, because unfortunately we don't have this kind of facility in India. Still, I am pushing and I established one at BHU. I tell you that this is the first facility in any university system in India. Other than BRC, you will never nowhere get this facility. So we are using this facility. So I will just show you something interesting, how we produce neutrons and how we do this scattering, elastic scattering studies. So this is how your charge particle accelerator looks. This is the building, and we have inside this one just to protect it. So we have a iron shield, and to make safe everything, we have this building so that it could look nice also. So I will skip this thing, but I just want to brief. This bottle is producing your proton. Basically, this is filled with hydrogen, and this is known as ion source in our accelerator. So on the top here, so you just imagine a kind of CFL tube. It is exactly of the same size. You fill this with hydrogen gas. Just keep a filament around this tube, heat up, and your ionization will start, and you will have H plus. And because H plus has a positive charge, so you keep the exit point at a negative terminal, negative potential. So this negative potential will suck the proton, because proton has a positive charge. So it will come out from here, and then it is known as beam optics. So beam optics, particle beam optics, is exactly the same what we use in optics, the light ray. So from here to the end, my point is that the beam should be confined through straight line. So because if it will not be in a straight line, so it will scatter to the beam line, and there will be particle energy loss and the resolution loss, and reaction will take place in between before the destination where we are interested. So before showing this, I will show the picture how the beam lines looks. So this is the beam line. So basically behind this you have this tower. This tower is behind this wall. So we are getting protons from here, 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 here. These are the gate walls. Suppose you have some trouble, so you just block this. So the beam will be earlier. It will not come on this side. So you are coming here, 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 and up to this point. Here you will see a very fine 3 centimeter stainless steel picture. I will try to show in next one if I, yeah. So this is the one. So just see this. So this is exactly the same thing what I'm showing here. So I'm trying to show you in the zoom. So up to this point you have a proton beam, and this is filled with tritium. And the beauty of this setup is that this is in gaseous phase. So you can make any kind of pressure, whatever pressure you want, you can make. So when I say gas pressure, so it is the kind of whether you are increasing the density of gas inside this 3 centimeter stainless steel or you are decreasing it. So if I am say that the gas pressure is high, so that means the vessel is crowded, the density of gas is high. That means the interaction of this proton with tritium will be very high. So that means that the neutron will be at a higher rate, but that will make impact on the shape of your neutrons. The quality of resolution will be slightly degraded. So as a experimentalist, you have to see whether you are interested in quantity or quality. If you are interested in quality, there may be a group, he is interested in quality. So he will say, भाई साहब मेरा गैस प्रेशर आप कम दीजिए, मुझे कम चाहिए बट अच्छा चाहिए, मुझे फाइन बीम चाहिए. जब मैं कहता हूँ अच्छा चाहिए, अच्छे का मतलब यह है कि स्प्रेड कम से कम हो. स्प्रेड हम ऐसे बताते हैं, अगर कम स्प्रेड होगा तो आपका बीम ऐसे चलेगा, बट इफ यू हैव हाई डेंस तो आपका फिर स्प्रेड होना शुरू हो जाएगा. सो देन यू विल गेट योर बीम लाइक दिस. तो आप अपनी बुलेट चाहते हैं मेरी बुलेट शार्प हो, मुझे वो बंदूक वाली गोली नहीं चलानी है जो छर्रे के साथ चलती है, मुझे चाहिए जी पॉइंटेड वन, क्योंकि जितना पॉइंटेड होगा मेरा उतना वो मेरे जो टारगेट को है वो एग्जैक्टली प्रिसाइसली शूट करेगा. बट देयर में भी सम ग्रुप, बहुत सारे लोग होते हैं जिनका रिसर्च इंटरेस्ट होता है कि भाई उनको हाई फ्लक्स चाहिए, उनको उससे कोई मतलब नहीं है कि कितना उसका रेजोल्यूशन है. सो इट डिपेंड्स. सो दिस इज द चॉइस ऑफ ए एक्सपेरिमेंटलिस्ट विच वे ही वांट टू गो. तो इसमें दोनों लिबर्टी है. सॉलिड टारगेट अगर आप ट्रिशियम का लेंगे, सो द प्रॉब्लम इन दैट इज दैट यू हैव टू चेंज एवरी टाइम. कोई कहेगा मुझे इतना चाहिए, कोई कहेगा इतना चाहिए, तो उसमें प्रॉब्लम है। इसमें क्या है, यू हैव हियर इन द बेड, इट इज द ट्रिशियम गैस इज एनलाइटन विद यूरेनियम बेड। आप उसको हीट कीजिए, यूरेनियम बेड को, वो एवोपरेट होकर ऊपर आना शुरू होगा, यहाँ गेट वाल्व है, यू टेक इट वट एवर गैस प्रेशर यू वांट टू टेक इट। जब आपका काम हो जाए आप उसको वापस भेज दीजिए, फिर वो वहाँ पे हो जाएगा, तो प्रिजर्व भी रहेगा विदाउट ए टाइम लॉस। यू कैन मैनेज, अच्छा जी भाई साहब मुझे इतना चाहिए, आई एम हैप्पी विद दिस गैस प्रेशर। बट अगर टारगेट सॉलिड होता तो पहली बात तो यू हैव टू प्रिपेयर द टारगेट्स, और आप कितने बनाएंगे एज ए एक्सपेरिमेंट, बिकॉज यू हैव ए फिक्स टाइम ऑफ एक्सपेरिमेंट। सो दैट इज द ब्यूटी ऑफ एक्सपेरिमेंटल gaseous tritium target, that you can change the gas pressure and you can play with the resolution or the number of neutrons coming out from the tip of the gas cell। तो भाई साहब यहाँ से आप, ये ट्रिशियम आपका भरा हुआ है, ये प्रोटॉन हिट करेगा, यहाँ पे घुसेगा इसमें, तो आपका न्यूट्रॉन पैदा होगा। अब यहाँ से क्लासिक स्टोरी जाएगी, आप बिल्कुल देखते रहिए, सुनते रहिए, अगर बोर नहीं हो रहे हैं तो। और अब मैं आपको बैक स्लाइड पे लेके जाऊंगा, जस्ट इसको आप दिमाग में रख लीजिए अपने कि ये कहानी क्या चल रही है हमारी, यहाँ तक ये प्रोटॉन आ रहा है। अब हम आगे चलेंगे और मैं बैक लेके जाऊंगा जिस स्लाइड को मैंने आपको छोड़ दिया था कि इस पे मैं वापस आऊंगा। तो देखिए क्या हो रहा है, ये वही हो रही है जहां से मैंने कहा था कि प्रोटॉन आपका घुसना चाहिए। सो दिस प्रोटॉन इज एंटरिंग इन दिस गैस सेल। मैं फिर से आपको लेके जाऊंगा, तो यहां से इट इज एंटर्ड और ये एग्जिट पॉइंट है, यहां से प्रोटॉन घुसेगा, यहां से न्यूट्रॉन निकलेगा। ओके, सो गो बैक। अब मैं सर फिर से एक अंतर पूछना चाहूंगा, अब एक अंतर बता दीजिए, ये मेरी एक खिड़की है, ये मेरी दूसरी खिड़की है, इनमें अंतर बता दीजिए, ये तो कोई भी बता देगा। What the difference you see in this 3 centimeter stainless steel tube on one side comparative to another side? ये एक विंडो है, ये एंट्रेंस विंडो कह लीजिए, एग्जिट विंडो, इनमें बस आप फर्क बता दीजिए, इसमें तो कोई भी फिजिक्स नहीं है, नो फिजिक्स, कोई भी बच्चा बता देगा। एनीबडी? सर मैं किसी का फेस नहीं देख सकता, मुझे तो आवाज सुनाई दे रही है, तो कोई भी बता दे, आई कैन नॉट रिकॉग्नाइज हु इज। नो फिजिक्स, एनीबडी? हाउसवाइफ भी बता सकती है, मैं मेरे ख्याल से दे कैन टेल। तो कोई फिजिक्स नहीं है सर, जरा अंतर बता दीजिए आप। हियर एंड हियर, एनी डिफरेंस? आई एम सरप्राइज्ड यू आर नॉट सीइंग एनी डिफरेंस।
सर एक बंद है, एक खुला है।
नहीं, दोनों खुले हैं जी,
दोनों खुला है,
दोनों खुले हैं। नहीं, अभी खुले बंद की बात नहीं करते, चलो अच्छा खुले बंद की बात नहीं करते। और उससे भी आसान अंतर है, तो तुमने बहुत मुश्किल आंसर दिया, क्योंकि खुला बंद का नहीं पता चला। थोड़ा सा और आसान आंसर बताइए। Sir, the difference is this is yellow color, this is white color. So this is intentionally made. Actually, the point is protons are not very penetrating particles, right? So you will make a thinner window. बहुत थिन विंडो आप बनाएंगे यहाँ पे। और ये जो व्हाइट वाली है, ऐसा नहीं है कि कलर से वहाँ पे वो दोनों साइड स्टेनलेस स्टील का है। यहाँ आप ऐसी एंट्री बनाएंगे कि प्रोटॉन घुस जाए आपका। आप चोर को घुसने का रास्ता दे रहे हैं घर के अंदर अपने, बट बिकॉज ये जो चोर है आपका, ये सीधी सीधी डायरेक्शन में चलेगा, ये इसके पास यू टर्न नहीं जानता बेचारा है, ये तो एनर्जेटिक पार्टिकल है, सीधा सीधा चलेगा जी। तो आपने इसको लालच देके घुसा लिया, लेकिन यहाँ पे आप इसको निकलने नहीं देंगे, ये जो व्हाइट वाला बनाया। तो यू मेड इट ए थिकर विंडो। वो क्यों बनाया? वो इसलिए बनाया सर कि जब हम प्रोटॉन को ट्रिशियम पे हिट करेंगे तो मुझे हीलियम का आइसोटोप मिलेगा और न्यूट्रॉन मिलेगा। और ऐसा भी हो सकता है कुछ प्रोटॉन आपका ट्रेवल करके यहाँ तक आ जाए, तो अब ये यहाँ पे गेट पीटता रहेगा, लेकिन ये निकल नहीं पाएगा। वही सिचुएशन हीलियम की होगी, क्योंकि हीलियम तो इससे भी भारी है। तो हीलियम और प्रोटॉन तो गेट के पीछे कैद हो गए हैं, और न्यूट्रॉन भाई साहब हवा में लहराते हुए निकल जाएंगे, क्योंकि उनकी कैपेबिलिटी है, वो इस गेट से ट्रांसमिट कर सकते हैं। तो ये मेरी बड़ी एक क्लेवर ट्रिक रही कि मैंने इसको घुसा लिया, अपनी रिएक्शन कराई, पी ऑन लिथियम एंड आई गॉट ए न्यूट्रॉन, और इसको मैंने ट्रैप कर दिया अंदर, बिकॉज आई एम इंटरेस्टेड ऑन न्यूट्रॉन। मुझे तो न्यूट्रॉन चाहिए था, मुझे तो कोई मतलब नहीं जी प्रोटॉन से और आपके हीलियम आइसोटोप से। सो दैट्स इट। तो यहाँ पे मैटर करता है, देखिए जो चीज मैंने बताई कि आपका गैस प्रेशर कितना है, उस पर डिपेंड करता है कि आपका बीम स्प्रेड कितना करेगा। तो 1.75 न्यूट्रॉन है मेरा, तो मुझे देखने पैरामीटर कि भाई मैं कितना कर रहा हूँ। तो 1.7 और 3.19 पे हमने दिखाया कि कितने कितने स्प्रेड होते हैं। एंट्रेंस फॉयल है, इस पर कितना स्प्रेड होगा तो जरूर, आप खिड़की तो तोड़ रहे हैं ना किसी के घर की, तो कुछ तो एनर्जी लॉस होगा। तो वो आपका लॉस यहाँ पे हो रहा है। गैस प्रेशर कितना है उसके हिसाब से एक एटमॉस्फेयर पे 81 केवी का आपको लॉस होगा अगर आप 1.75 MeV न्यूट्रॉन प्रोड्यूस कर रहे हैं। तो दीज आर द थिंग्स एज ए एक्सपेरिमेंटलिस्ट यू हैव टू सी। तो जब ये न्यूट्रॉन आता है तो ये आपका ये पूरा सेटअप है, ये शील्डिंग है, यहाँ आपका न्यूट्रॉन डिटेक्टर बैठा हुआ है। तो ये आपका इसको हिट करेगा, ये टारगेट है आपका। तो ये आपकी स्कैटरिंग है, यहाँ से स्कैटरिंग होगी और आपका पार्टिकल जाएगा। सर हाउ मच टाइम आई हैव, मेरे पास उसी हिसाब से मैं उसको प्लान करूंगा। आप कितना टाइम देंगे? मेरे पास बहुत है, आई कैन स्पीक 2 hours, बट आप मुझे बताइए कि हाउ जनरस यू आर।
Sir, 5 to 10 minutes.
बस, अरे
Oh,
ओके
yes, sir.
ओके ऑल राइट
Because-
सर। No, 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 it's fine, it's fine.
Okay.
So it will hit to this target and the scattering will take place. जब हम scattering की बात करते हैं ना, तो we have gone through in our graduation day or +2 day, so it is like billiards game. हम जो कंचे खेलते हैं, that's a perfect example of scattering. वहाँ पे आप देख सकते हैं। तो same thing happens from this also. Neutron will come out and hit to this, and after hitting you will have two things. इलास्टिक भी हो सकता है, इलास्टिक भी हो सकता है, क्योंकि जब न्यूक्लियर फिजिक्स में हम बात करते हैं तो एक प्रोसेस नहीं होता। हम ये देखते हैं कि प्रिफरेबल प्रोसेस क्या हो रहा है। अगर मुझे फ्यूजन देखना है तो फ्यूजन होना चाहिए, फ्यूजन भी होगा, बट फ्यूजन हो सकता है कम हो। तो मेरा इंटरेस्ट फिशन में है, तो मैं फिशन की कंडीशंस क्रिएट करूंगा जहां पे मैक्सिमम फिशन हो। आई विल नॉट गो फॉर फ्यूजन। पता चला कि आपने कैलकुलेशन ही नहीं की, इंटरेस्टेड फिशन में थे, डोमिनेट फ्यूजन कर गया वहां पे। तो यहाँ पे दोनों ही प्रोसेस होंगे, मैं उनको दोनों को स्टडी करूंगा। तो उसको स्टडी कैसे करूंगा? मेरा न्यूट्रॉन डिटेक्टर बैठा हुआ है जी वहाँ पे, ये मेरा न्यूट्रॉन डिटेक्टर बैठा हुआ है, यहाँ पे मैं स्कैटिंग देख रहा हूँ, ये सारा शील्ड है। टाइम ऑफ फ्लाइट मेजरमेंट करते हैं। न्यूट्रॉन क्योंकि चार्ज नहीं है, तो मेरे पास उसकी एनर्जी मेजरमेंट करने का तरीका क्या है? 1/2 mv²। m मास है न्यूट्रॉन का, v वेलोसिटी है। अब वेलोसिटी कैसे निकालूं मैं? मेरे पास डिस्टेंस पता है मुझे, और मुझे पता है कि v = d/t। तो मेरे पास डिस्टेंस है, तो ये मेरा फ्लाइट पाथ हो गया। दूर रखने का फायदा क्या है कि आपके न्यूट्रॉन्स क्लियर रहेंगे, बिल्कुल मैसअप नहीं होगा। कोई अगर आपका फ्लोर से दीवार से टकरा के आ गया तो वो कंट्रीब्यूट नहीं करेगा। सो दिस इज द ब्यूटी ऑफ दिस सेटअप। और आप अपना इलास्टिक और इनलास्टिक स्कैटरिंग यहाँ पे डिटेक्टर में रजिस्टर करा पाएंगे। टारगेट्स कैसे होते हैं हमारे स्कैटरिंग के लिए? हमेशा थिक टारगेट यूज किया जाता है। इफ यू विल सी एनी स्कैटरिंग एक्सपेरिमेंट, सो यू विल सी थिक टारगेट्स। सो यू सी वेरी थिक टारगेट। इफ आई विल यूज ए फ्यूजन रिएक्शन, तो जो आप मिठाई खाते हैं बर्फी के ऊपर चांदी का वर्क लगा रहता है, तो उस दैट काइंड ऑफ थिकनेस वी यूज फॉर फ्यूजन रिएक्शन। तो अगर आप इसको बना देंगे फ्यूजन के लिए, तो आपका एक्सपेरिमेंट शुरू होने से पहले ही बंद हो जाएगा। सो दिस इज द प्रोसीजर ऑफ इलास्टिक स्कैटरिंग एक्सपेरिमेंट। ये आपको दिखाता है कि आपका पूरा का पूरा सीधे आपके डिटेक्टर में जा रहा है कि नहीं। तो वो भी आपकी डिजाइनिंग जो हमने यहाँ पे दिखाया अपना सेटअप। सो दिस इज वेरी कॉम्प्लिकेटेड, वी हैव टू डू इट। I have to spend something like 48 hours to set this direction so that everything is passing through this structure up to the neutron detector. Because if you are losing something, so that doesn't make any sense of measurement. अगर आप मिक्सअप करके करा रहे हैं, क्योंकि टारगेट तो आपका यहाँ था, you are interested only in the scattered particles coming out from this target. इसके अलावा कहीं भी आपका हिट करेगा उसमें आप इंटरेस्टेड नहीं है। तो for that you have to make sure experimentally as well as through some simulations done by MCNP program. So ये मेरी सिमुलेशन बताती है कि जी आई एम गोइंग परफेक्टली ऑल राइट, और मेरा सारा रजिस्ट्री इस बैठे हुए जो डिटेक्टर न्यूट्रॉन डिटेक्टर इसमें हो रहा है। तो दिस इज काइंड ऑफ मेजरमेंट ऑफ न्यूट्रॉन्स कमिंग फ्रॉम इलास्टिक एंड इलास्टिक स्कैटरिंग। ये फिर हम एफिशिएंसी करते हैं, इसकी कोई जरूरत मैं नहीं समझ रहा अभी क्योंकि टाइम मेरे पास कम है। ये अटेन्युएशन का होता है, जब भी आपका टारगेट आप लेते हैं तो आपका पार्टिकल उसमें अटेन्युएट करता है, उसको स्ट्रगल करना पड़ता है, तो उसका भी आपको करेक्शन फैक्टर लगाना पड़ता है। हर कोई करता है जो भी कहीं रिसर्च करता है, तो अटेन्युएशन को आप टेक केयर करते हैं। I think I will stop here because the next one is a topic which will need again 30 minutes. So I will be happy to go for question answer session. जी सर, आई एम डन। अगर आप चाहते हैं तो फिर मैं नेक्स्ट टॉपिक पे जा सकता हूँ, इफ यू हैव टाइम। तो देन आई नीड एटलीस्ट 15 मिनट्स। ये दिस इज माय सेकंड प्रोजेक्ट। आई हैव ए इंडो रशियन प्रोजेक्ट, सो आई एम वर्किंग इन JNR. We have established a facility known as Tangra. So I can go if I have 15 minutes. Otherwise, it will not be in a complete form. So you have to tell me, should I start this or are you okay up to that point?
Sir, you can summarize your talk within 10 minutes.
Okay. So here what you saw is the neutron scattering at this Venn diagram facility. Here I will show just to make your measurement more precise. So this is known as tag neutron facility. So here you have another mechanism to produce neutron. It is on tritium. When you shoot neutron, so you will get neutron again. So this is second type of reaction what I showed. The beauty of this machine is that you will get your neutron in triple coincidence. So when I say coincidence, so coincidence means when you have a DT reaction, so there will be some kind of alpha production and neutron production. So when you will have this alpha detection in alpha detector, and the same time you will have a neutron, so that will make sure that the neutron you are getting is corresponding to this reaction. So there are two registry, one of alpha, इस डिटेक्टर ने अल्फा को पकड़ा, इसने न्यूट्रॉन का सिग्नल दिखाया। तो ये आपको इंश्योर करता है कि आपका जो रिएक्शन प्रोडक्ट आया अल्फा और न्यूट्रॉन इस रिएक्शन से आया। सो नाउ दिस न्यूट्रॉन विल हिट टू द टारगेट ऑफ इंटरेस्ट। तो वो आपका ट्रिपल कोइंसिडेंस होगा व्हेन यू विल हैव ए क्लिक फ्रॉम दिस अल्फा, क्लिक फ्रॉम दिस न्यूट्रॉन और क्लिक फ्रॉम दैट गामा। So that makes it triple coincidence data, but the problem with this data is that the rate is very slow. जो चीज आप पहली फैसिलिटी मैंने आपको दिखाई आप 8 घंटे में कर सकते हैं, वो चीज आप यहाँ पे 8 दिन में करेंगे। तो द पॉइंट इज अगेन सेम दैट व्हाट इज योर इंटरेस्ट एग्जैक्टली एंड व्हाट आर योर लिमिटेशन आल्सो। मैं कहूँ कि जी मुझे तो ऑडी चलानी है लेकिन ना मेरे पास पैसे हैं ना मेरे पास सड़कें चलानी है, तो कोई फायदा नहीं है भाई फिर, है ना। तो आपको ये देखना पड़ेगा कि व्हाट आर योर कंस्ट्रेंट्स। सो इन दिस टैग न्यूट्रॉन स्पेक्ट्रोस्कोपी I can get the very high quality neutron. When I say high quality means it is coming from your original reaction. देखिए होता क्या है कि you got this neutron, ये न्यूट्रॉन कहीं भी जा सकता है, आप देखते नहीं है, we cannot see the particles, तो ये कहीं भी जा सकता है, दीवार पे लग सकता है, कहीं इक्विपमेंट पे टकरा के फिर रजिस्टर कर सकता है आपके टारगेट के साथ। So you lost your original neutron. So just to make sure that you are getting results from your original neutron coming with this reaction, you make this tag neutron spectroscopy. तो इसका फायदा यही है कि इसमें अल्फा आपका अल्फा डिटेक्टर में चला जाता है, न्यूट्रॉन न्यूट्रॉन डिटेक्टर में चला जाता है और उसके करस्पॉन्डिंग फिर आप गामा देखते हैं। सो ये चीज आपकी वहां मिसिंग थी, अगर आपके याद हो यहाँ पे मैंने दिखाया था, तो आप अल्फा को रोक लेते हैं यहाँ पे। बट इस सेटअप में हमारे जो टैग न्यूट्रॉन स्पेक्ट्रोस्कोपी है ये आपका न्यूट्रॉन जनरेटर है। तो ये सब हम लोगों ने एस्टेब्लिश किया, डुबना रशिया जाके मैं और मेरे स्टूडेंट जाते थे, तो वी एस्टेब्लिश दिस एरे ऑफ डिटेक्टर्स। तो यहाँ से न्यूट्रॉन निकलेगा, पीछे की तरफ अल्फा जाएगा, तो दोनों का क्लिक हुआ, आया, वो कहेगा मेरे पास अल्फा आया, न्यूट्रॉन डिटेक्टर कहेगा मेरे पास न्यूट्रॉन आया, उसके करस्पॉन्डिंग आपकी टारगेट को हिट करेगा जब न्यूट्रॉन गामा आएगी। तो वो 3 सिग्नल जब होंगे तो कहेंगे दिस इज द राइट सिग्नल, यू टेक इट। सो दिस इज द क्वालिटी। सो देयर इज नो लिमिट ऑफ क्वालिटी व्हेन यू गो फॉर प्रोवाइडिंग डाटा to a sensitive group of reactor people. So you have to be very precise. So that is the logic. So in summary, I want to conclude that today I talk about kind of scattering, taking from Raman Sahab research, and then I converted my topic. He talk about photon scattering in terms of Raman scattering, inelastic scattering process. I connected it with my work, what I'm doing with neutrons in terms of elastic and elastic scattering, and we pick neutrons and we stop alpha in one goal, and to make it more precise we open the way for alpha particle also, neutron also, and we made a triple coincidence, but the acquisition rate will be slower in this triple coincidence comparative to where we stop the alpha particle. So the concluding thing is that neutron is the fundamental tool to provide neutron cross-section data, whether it is elastic or inelastic for reactivable. And tag neutron spectroscopy is able to provide very high quality data, right? Because you are not supposed to provide all the time data, like I am working in neutron field, so I am supposed to provide all the data to all new international community. If you are comfortable and if you are getting the data up to that quality, you are sure, okay, I don't have money to make this Russian facility here, so I cannot promise that my data is of equivalent quality what I am getting from Russian facility. So no, so you have to tell that this is the level of precision in my data, and this is the precision when I am getting from my Russian facility, and this is from my American, this is from my Indian facility. So that is a very crucial part in my research paper or anybody research paper, that they have to mention strictly what is the level of accuracy. Then it will be used accordingly to the deserving place. So that's it. Thank you very much, sir. Thanks to all, and thanks for providing me this opportunity. I tried my best. I don't know how much I was capable to convey my things. Thank you. जी sir, done.
Sir, it's the time for the questions.
Very much, sir. मैं तो बीच में ही तैयार था लेने के लिए ना.
Okay, sir.
Yes.
Yes, anyone have a question? Any question? Okay, sir. Sir, nuclear reactions in terms of the low energy, high energy, and intermediate energy range. In
Ji.
India, we have opportunities up to which one values we have conduct the perform just like BRC, BHU, and many more. What is the facility up to the energy level in India?
Sir, right now, what I know in my best knowledge, we have one facility for university user at New Delhi Inter-University Accelerator Center. So
Okay.
any person from institution, whether engineering institution, IIT, university, can contact to the person of his interest at IUAC, and he is able to defend his proposal. He will get all the support from IUAC Delhi for local stay, travel, and if you are able to successfully defend your project, so you will able to use the facility. Second one is at TIFR, that is in collaboration of TIFR and BRC. So there you cannot enter directly, you have to take care of somebody from BRC or TFR. He will be the PI, and then with the help of that, it will be your idea, your proposal, but he will defend it because it is their personal thing between TFR and BRC. IUSC thing is open totally for anybody. Anybody can come and use it. Then we
Okay,
have
thank you, sir.
have variable
Thank
energy.
you. Thank you.
Yeah.
Sir, it's the time for the vote of thanks.
Okay.
A warm and grateful morning to our students and colleagues and most valued person, our esteemed institutions, IIMT College of Engineering, Greater Noida, our director, sir, all deans and all HODs. I, Dr. Pankaj Kumar Sharma, IIC coordinator, on behalf of IIMT College of Engineering and the entire fraternity of the institution, first of all, extend my most sincere thanks to the Almighty God for making today's event a resounding success. With his blessings and grace, we are able to make this event what it was. I really extend a hearty vote of thanks to our today's eminent speaker and renowned name of India and international level, Professor Ajay Tyagiji from BHU Varanasi, for wonderful speech on National Science Day. Thank you very much, sir, for enlightening our students and give me valuable time for your end. Thank you very much, sir.
Thank you, sir. Thanks.
Thank
It was
you.
a pleasure to
Now
have.
it's time for the leaving the meeting. So have a nice day and congratulations to all which have patience and discipline enter the event. Thank you very much, sir.